start recording and share my screen. I will share my screen as soon as I can find my PowerPoint. There we go. So this is already week 8. We're almost done with the semester. I don't know. Time flies, as they say. And we started last week this section, the last section in the course on modeling and simulation. And we left off just before parameter estimation. So we will continue with that this week. We will talk about what is involved in estimating the parameters of a model, what do you have to be aware of? Can you always find a close expression for the parameters? Do you sometimes have to use numerics, and so on? And then on Thursday, you have a PC practical on this topic, where you will, for a given class of models, learn how to estimate the parameters within R using some built-in R commands. And if you've seen my announcement, then we've had to make yet another, and hopefully now really this is the last change to the rooms for the PC practicals. So the people that were previously in B1, now please go to room 202. Why did we have to change it? Well, there were continuing issues with climatization in B1. Was either way too cold, or I think it'll become way too hot in a few weeks from now. So we decided to move the class to a room with better climate control, basically. So hopefully you won't have to freeze again once you're in 202. So the people that are in B1, just go to room 202 on Thursday. The people that are in room 203, nothing changes. So the people that are with Negin go to room 202. The people with Abiodun stay in room 203. The slide that I've shown last week as well. We're halfway through with April. We're right in the middle of chapter 10. We might be able to finish that today, but if not, we have a bit on the schedule set aside for that next week. And so these are the 4 weeks. Then week 10, so not next week, but the week after that is the next exam week that you have. There will be no class during that period. And then there's 2 more weeks. So actually, yeah, not that much class left in the semester once again. And then one last practical announcement that I made last week. So I just took over this slide verbatim from last week. So we are supposed to have a question and answer session today, 19th of April. So I didn't get many questions. In fact, I got none, which makes it a bit awkward to have a Q&A session. We will have another Q&A session probably during the catch-up week. But what I would do for today is I will briefly go over 2 questions from the exam during the last half hour. So in the absence of questions from you, I will pick some questions of my own, and then we'll talk about that. Okay, so those are all the practical announcements that I had to make. Then it is time for us to go back to parameter estimation. As you saw from the email that I sent out last night, or that you probably read this morning, I've made a couple of changes to the slide deck that I posted last week. So the part that was covered last week, that doesn't change. That's still the same. But the part that we're going to cover today, I've streamlined and hopefully made it a bit more easy to understand. We'll see about that. But it is important that you choose from Eufora, if you use the slide deck to follow along, choose the updated version. So I can maybe just briefly pull up my screen. If I stop the slideshow. And grab my browser. Here we go. Should be able to see my browser. So in underneath chapter 10 parameter estimation, in the content section, you should choose the slide deck 10 parameter estimation new, capital new. That's the one to use for today. Okay, so if you have that one, you're good to go. And I will share my screen. All right, there we are. So what we want to do now is, for a given model, we want to say something about how we can best determine the optimal value of the parameters that occur in that model. And as a quick reminder, what do we mean by parameters of a model? So last week we saw a couple of models in practice. So for instance, we had the Michaelis-Menten model, where the speed at which the product is produced depended on a maximum concentration and then a reaction constant and the concentration again. So in this case, these Vmax and Km are parameters of our model that a priori we don't know, that they will be different based on what particular enzyme, what particular substrate we have. So typically either we can look them up in a book or in a paper, or we have to measure them experimentally based on some data. So what we're going to do now is, for all these models, we're going to talk about if I have some data, like if I do an assay of how the product is produced, and I measure after instances in time, I measure how much of the product do I have. Given that experimental data, I'm going to try to find out what the optimal parameters are that correspond to that model. So for the Michaelis-Menten reaction, typically the reaction profile looks like this, with a horizontal asymptote. So if we ignore that for a second, and if we do measurements, so we put our concentration of substrate on the x-axis, and then we do a number of experiments where we change the concentration of the substrate little by little, and we measure the reaction rate, we may get something, some data points that look like this, and so on. So now what we'll try to do, and let me just choose a different colors, we'll try to find the best fitting curve that best matches those data points. And in doing so, we'll get an expression based on the data for the parameters of our model. So we'll use that to find K, M, and V max. And we've already done that when we talked about linear regression. So for linear regression, we did something like that already. So let's say we have some data points like this that, roughly speaking, look like they could be linearly distributed. Then linear regression was the problem of finding a straight line that best approximates these data. And how did we measure best approximates? Well, we looked at the residuals and we tried to minimize the sum of the squares of the residuals. And in doing so, we found the best fitting line, and that told us something about the intercept and the slope alpha and beta of the line. So what's different now between when we talked about linear regression? Well, now we're going to do this for general kinds of models, and they don't need to be straight lines. They can be curves in higher dimensions, surfaces, and so on. And we'll talk generally about what is involved in figuring out the parameters of a model. So in order to do that, we're going to have to say something about what do we mean by best fit, or what do we mean by a model fits the data well? Well, in what sense? And in order to do so, we'll define an objective function. So typically, you will either define this objective function yourself, or you will be given that objective function based on the class of problems that you're dealing with. And in general, this objective function can take on many forms, but it measures how well your predictions fit your experimental data. So for instance, for linear regression, we have an objective function, J, and I'll write something here, but I'll leave it a bit blank for the moment. And our objective function was basically, we said, okay, we want to minimize the sum, not of the residuals, but of the residuals squared. So we'll take the sum over all the data points. So let's say we have n data points, x1, y1, and so on, up until xn, yn. And we'll take the residuals. So we'll take the actual value, yi, and we'll subtract from that the predicted value. So for linear regression, that was alpha, the intercept, plus beta times xi. And then we'll take the square of that. So this right here, this is what we sometimes called y hat I. This is the prediction of the model. And we take the squares of each of those differences, and then we sum them all up, one for each data point, and then the sum overall. And now, what do we have here on the left-hand side? This gives us a function, which we'll typically call J. We'll use J for objective function. And what is that? So the name says it's an objective function. So what is a function of? Well, it is a function of the parameters alpha and beta. So if I plug in different alpha and different beta, then I'm going to get a different set of sum squares on the right-hand side, and the value of my function is going to change. But what I want to do for linear regression and also for higher models is I want to find the alpha and the beta that make this objective function as small as possible. So yeah, let me try to squeeze this in. So here, what we want to do, so goal of parameter estimation, find alpha and beta such that J of alpha and beta is minimal. And that's a mathematical prescription of what we try to do when we say in words, I'm trying to find the parameters so that my model best fits the given data. So what I've done is I've written down my model, linear or otherwise, and I've postulated an objective function. So for linear regression, I have that the objective function is the sum of the squares of the residuals. And now what I'm going to do is I'm going to try to find alpha and beta that make that objective function as small as possible, because smaller means better fit between the model and the data. And here once more, yeah, you have the picture of the residuals. This is for linear regression, but we will do something for more general models as well. So this is also summarizing what I've just said. So for linear regression, what we want to do once more is minimize the sum of the squares of the residuals. So by the way, here, remember, if you just take the sum of the residuals, then that will not do you much good, because you will basically get something, or will not work it out. So the sum of the residuals themselves isn't going to help you, because you don't really care about the sign of the residuals. You just want to know how far away is the prediction from the actual data point. And you want that distance to be minimized, but you don't really care whether that distance is positive or negative, whether it's under or above. So, and then here you have the same objective function as on the previous slide, where yi hat is alpha plus beta xi. And here, why do we have a theta and why do we have a beta? So in general, we will have many parameters in our objective function. We will have one argument for each parameter, and we'll use theta as a placeholder notation to denote all the parameters. And so here theta is basically the vector alpha and beta. And so what we will do is, in general, given our objective function, we'll try to find a minimum of it. So we'll try to find the theta vector that makes J as small as possible. And there's a few extensions here on the slide that I will briefly mention, but they're not that important. So if we have our objective function for one model, then we can concatenate several models equally well. If, for instance, we have several outcomes that we want to study at the same time. So here we have several outcomes, and we want to strike a balance between a model that can fit all of these outcomes for the same parameters. Then what we can do in our objective function is we can add a sum term for each individual outcome. So this is outcome 1, outcome 2, and so on. For instance, let's say I asked you to measure the width of your hand, remember, and also your height. And then we built a linear model to predict your height from the width of your hand. But now imagine that I said, also measure your weight and tell me something about your weight. In that case, I would have two outcomes. I would have the height and your weight and one predictor, the size of your hand. And now we could try to build a model that predicts both your height and your weight based on the width of your hand. And so we would have two outcomes and one predictor, and we would have to find parameters that basically link the width of your hand with both your height and your weight. And if you hear it explained in words, it's probably obvious what you have to do. If you can make a model for one predictor, you can also make a model for two predictors. You basically just add those objective functions together. And then down below, we have an extension here of what we would do if these outcomes have different measurement areas or different variances. Then what we can do is we can give each term in our objective function a different weight. So these are, you can interpret them as weights. So here, if sigma squared is high, then 1 over sigma squared is going to be low, because 1 over a big number is a small number. So the weight is low for outcomes that are associated with high variance. So let's say in the same example that I mentioned before, let's say we can measure our height very accurately by just by a tape ruler. So let's say up to plus or minus 1 or 2 centimeters, that's probably accurate. And let's imagine that for our weight, that's not the case. Let's say we can only measure our weight up to 5 or 10 kilos, so relatively noisy. Then what we would probably want to say is in our objective function, okay, my weight, that those terms associated with weight are relatively inaccurate, so give them less importance. Multiply them by a small number so that the noise doesn't dominate my objective function. Of course, to write down the objective function in this sense, this means that you have to know what the variance of your outcomes is, or you have to estimate it from your data. So that might be an additional data analysis step in your model. And one thing that's going to be useful for us, I'll just mention what's going on here, and then we'll skip over this. We will, in some cases, so the important thing here is the matrix notation. So in some cases, we will write down our objective function in matrix form, because it's easier to work with than always having to write that sum. So what we can do, for instance, is let's take our objective function that we had on the previous slide. So j is sum I is 1 up until n. And then we said, well, if the variances are all equal, we have something of the form yi minus yi hat of theta squared. And so we can write this as a vector y1 minus y1 theta, y2 minus y2 theta, and so on. And then times, so a row vector, and then times a column vector y1 minus y1 hat theta. So there should be hats here and here. y2 minus y2 hat theta, and so on, yn minus yn hat theta. And if we so you can multiply this row vector by the column vector, and you'll see what you get is precisely this sum of squares. And what we can also do is we can make this a bit more interesting by putting a matrix in between the row and the column. So here, if I take this Q matrix and I put this in between the row and the column, then basically what I get is not a lot of space. So let me just write it down below here. So what I will get in that case is y1 minus y1 hat theta, and so on, yn minus yn hat theta. And then this Q matrix, it's a diagonal matrix, so I can just write down the diagonal elements, 1 over sigma 1 up until 1 over sigma n squared, and then times this column vector y1 minus y1 hat, yn minus yn hat. And now if you multiply this matrix by this column, what that will do is it'll multiply each element in the matrix, in the column vector, by 1 over sigma I squared. And then if you multiply that whole thing by the row vector that I have here, you'll end up with, again, a sum of squares, but where every term in the sum is weighted by 1 over sigma I squared. So I'll leave it to you to do that matrix multiplication, and what you will get is the expression that we had on the previous slide, this expression right here. And this is just bookkeeping at this point. It's just a different way of writing the objective function, and one that's going to be easier to handle in what follows. So that's the objective function. So let's put that aside and move on to the other things that we need in order to do parameter estimation. So the next thing is we have our objective function. We can measure what a good model is versus what a not so good model is. The next thing is we're going to need data. So we want to fit the model to the data, so we need data. And there's a subtle but very important point here, and that is we're not going to need one data set, we're going to need two data sets. Why do we need two data sets? Well, you can imagine, well, hey, if I have some data, I can go ahead and I can try to fit that curve through the data. And that's what ultimately we will want to do. But what we want to do as well is we want to set aside some of our data for validation purposes. And what does that mean? Well, we will want to use the bulk of our data for fitting the model, but then we want to have some data that we set aside to see how good the model fits the data. So validation here means we want to test or we want to figure out how good the model is on new data. So to check how well the model does on new data that we've never seen before. And intuitively, you can probably imagine why that's important. Well, if I just make my sketch, if I have some data points, and I try to find a curve through that data, let's say, then what I'm going to do is I'm going to wiggle those parameters of the curve as much as I can to get the best possible fit to the data. But that means that my parameters are very attuned to the data that I'm given. And now if I say, well, hey, look, my model fits the data so well, then what I'm doing is I'm being actually a bit too optimistic about how my model or how my model is fit. What I should do in order to have an honest comparison is I should set aside some of the data that I never look at during the model fitting. I should do my model fitting on the rest of the data and then come back to this validation data set and check, okay, on the validation data set, how well does my model do? And if I have a good agreement with the validation set, then I can be confident that my model is a good model on unseen, on held out data. And this is something that you will also see if you do, for instance, machine learning. So in machine learning, you do nothing basically but fitting models to data. And there also the first step that you do is when you train a neural network or a support vector machine is you set aside some data, 20%, 30%, and you never look at it again while you build your model. And then once you're done, once you say, okay, this is my trained neural network, and I'm happy with that, then you grab the validation data set and you say, how well does it do on this held out data? Maybe just to give you one more example, an intuitive one is, let's say you want to assess for yourself how well you're going to do on the statistics exam. And one thing that you can do during your study is you can look at the exams of past years. And while you're studying, you can take these exams. So you solve the exam and you say, oh, wait, there's a question about hypothesis testing here. And I totally forgot that. So I'm going to go back and study that. So you go and you study the hypothesis testing section, and then you look at the exam again and you fill everything out correctly. If you keep doing that, you keep studying and looking at the exams, then after a while, you're going to be very good at studying these old exams. Like you're going to get a perfect score because every time you don't know something, you can look it up and get better. But you probably wouldn't say, hey, I'm an expert statistician and I'm going to score 20 on every statistics exam. You would know that the real test in whether you understand the material is to take an exam that you've never seen before and then see what your performance is on that. And this is exactly the same thing. We give the model some data to train on, and it can do whatever it wants with the data. It can just internalize it and fit the parameters as well as it can. And then in order to assess how good the model really is, we give it some new data and then check what happens there. And you will see typically that the model will score a little bit less well on the validation set than on the training set. Just like if you studied with the help of exams, after a while you would score 20 on these practice exams because you've looked at them so many times. But then if I gave you a new exam that you haven't seen before, even if you know the material really well, you probably wouldn't score 20 unless you're very lucky. You score maybe an 18 or a 17 or 16, slightly lower, but still good. And then here too, we would say, okay, your score on a new exam is 16. So that is probably representative of your knowledge of statistics. So that's a long story about why you need this split into calibration or testing data. That's to train the model on, to estimate the parameters on, and then validation is to check how well the model does on new data. And when you split the data into two different sets, so and typically here the testing or the calibration data set will be quite large, on the order of probably like 80%, with the validation set smaller, 20%, 30%, 15%. So typically you do want to use a lot of data for calibration, for fitting the parameters, and a good but not huge data set for validation. The exact percentages depend a bit on the application in question, but the vast majority goes towards calibration, parameter estimation. It's also very, very important that these sets are independent of one another. Why is that? Well, if I have data points in my validation set that also occur in my calibration data set, then again, I'm going to artificially inflate the performance of my model. Then it's a bit like if I give you a new exam of statistics, but it contains old questions that you've already seen, you're going to get a boost on those questions, and that's going to inflate your performance. So we want the calibration and the validation set to be independent of one another as much as possible. And this is a very tricky point in some cases. So for instance, if you build models that do something with biological sequence data, then typically biological sequence data is highly redundant. If you do some sequencing experiment, for example, you'll get many, many reads, and they will be there will be many, many duplicates. So let's say, for instance, you do a gut microbiome experiment. You take a stool sample from a patient, and then you sequence the genomes of the bacteria in that sample. You're going to get many of the same kind of bacteria. You're going to get E. coli, lactobacillus, whatever, sort of very common bacteria in high abundance. And then there's going to be a long tail of very rare bacteria. And now if you just take the data from that gut microbiome sample and you naively split it in 80% validation, 80% calibration and 20% validation, then chances are that your two data sets are not going to be independent. It might be that there's a lot of E. coli in both the calibration data set and in the validation data set. And in that case, you have a problem because now, okay, your model will learn how to detect E. coli, let's say, or do something with E. coli, and it'll get very attuned to E. coli. But when it comes to validation, it'll also see those E. coli in the validation data set, and it'll know how to do well on those as well. So you need to make sure those data sets are independent as much as possible. And likewise, the validation data set needs to be, the calibration data set needs to be broad, needs to have enough information to actually fit your data well on. And I just see a question in the chat. Yeah, so maybe just one thing about terminology. Okay, how do I get rid of this? Okay, so here the question is, so we say test set. Let's maybe change this terminology and let's call this the calibration data set. So then here we can also say this is the calibration data set. That's the thing that you train on. That's what needs to be broad, have all the experimental conditions so that your model can sense what's going on and needs to be of good quality. And if you do machine learning, this is also sometimes referred to as the training data set. And then the validation data set is the one that you do validation. So now that we have our objective function, now that we have data, we need to say something about the parameters that we want to estimate. For linear regression, that was easy. If it's simple linear regression, we only have two parameters, the slope and the intercept, so there's not much of a story. But in general, if we have a complex model, so imagine, for instance, we want to say something about a model describing a bioreactor. We may have many different parameters that can affect that can be at play in the model of our bioreactor. We can have something about the parameters that determine the chemical reaction that goes on in the bioreactor or reactions. So we might have some kinetic rates. We may also have something having to do with the boundary conditions of the bioreactor. Maybe we keep that reactor at a certain steady temperature that we can either measure or leave unknown and that might have an effect on the chemical reactions that take place in it. So we could, for instance, treat the temperature at the walls of the reactor also as an unknown parameter to be estimated, or we could take even the initial conditions of the bioreactor as a parameter. So let's say the reactor has been in operation for some time, and now we want to do an assay or an experiment to characterize something about its working. So we take some samples from the reactor and we observe a given concentration of a product in the reactor. And we know that that reaction must have started with some initial concentration, but it was a long time ago, last week or last month, and we failed to record it for whatever reason. Then we could also, for instance, include that initial condition as something to find out a parameter, to determine from the data. So here we can have initial conditions, or also boundary conditions. There's always a trade-off. However, if you have more parameters, then you have basically more work to do, which basically will make it harder to fit your model, because typically if you have a fixed size data set and you want to estimate a lot of parameters, you will have less data points per parameter, if you can sort of quantify it like that, than compared to only having to fit one or two. So if you have more parameters, it'll probably mean that you will have less certainty when you determine those values about what the true value is. Likewise, if you throw everything into the mix that you can find, then you may run into the kind of trouble that we've seen in the section about linear regression, where we said if you have predictors that are highly correlated, that's usually a problem for the fit of the model, because what you want to do is, in your linear model, you want to determine what is the effect of each predictor on the outcome. But if two predictors are correlated with one another, then it becomes very difficult to distinguish the two. You don't know, okay, is the outcome associated with parameter 1 or with parameter 2, which happens to be correlated with it. So that can compromise your ability to find a unique solution, or can make it difficult to to find the parameters in the first place. So you might find that your computer software just gives up and says, okay, I'm sorry, but for this data set and for this model, I can either not find any parameters, like it just blows up, or here's a whole variety of different parameters that all fit the data equally well. And either is a bit of a problem, because typically what do we want out of parameter estimation? We want those fixed values, and we typically want to be confident about them, because then we can use them for predictions, for understanding the system, understanding associations, and so on. So what can you do when you want to select the parameters of your model? You can try to reduce the number of predictors or parameters that enter into your model based on a number of rules of thumb. One is you can, by whatever means possible, try to gauge the importance of a parameter. So next few lectures, we will see a set of techniques called sensitivity analysis, which will basically allow us to say, okay, this parameter, if we change this parameter a little bit, then the model changes a lot. So sensitivity analysis is going to tell us which parameters are important. So we will say that a parameter or a model is sensitive to a parameter sensitive to a parameter P if we move P up and down a little bit, if we change P a little bit, then the model changes by a lot. So if this happens, if changing the parameter a little bit makes the outcome of the model vary by a lot, then we say that the model is sensitive to that parameter. So these parameters will be important. And here we will want to include them in the model, because without them, or if we estimate them wrongly, then our model fit will not be good. And then, of course, an insensitive parameter is one where even if you jiggle the parameter by a lot, the model either stays constant, or the predictions from the model stay constant, or they don't vary that much. In that case, we say this is not such an important parameter. This is a nuisance parameter. This is a parameter that we can probably ignore. Where do you draw the cutoff between important and can be ignored? It depends on the analysis on the problem at hand. Could be, for instance, that you say, okay, my chemical reaction happens to be not sensitive to the temperature. If I change the temperature in my reactor by 5 degrees, 5 degrees positive or 5 degrees negative, then the outcome of my chemical reaction changes by 1 or 2%. But my boss or the manufacturer or the client has said that tolerance of 10% is still okay for this production process. So that falls within my tolerance, and therefore the temperature is not so important. Or you might have something the opposite, where you say, yeah, I have some contaminant that is produced by a reaction with a certain kinetic rate. And if there's even a tiny bit of contaminant, then my model or my outcome changes. In that case, you would probably that would probably give you an important parameter to include. So sensitivity analysis, we'll come back to that, gives you an idea of the relative importance of the parameters, and then based on that, you can make a judgment call. If I want to ignore something, can I ignore this parameter? Another thing that you can do is parameters basically don't come out of the blue. You typically don't start with a completely blank slate with no idea of what this parameter is going to be. Let's say a kinetic rate for a chemical reaction. You probably have some prior knowledge about what that kinetic rate is likely to be. You can look at a paper or a table of known chemical reactions in some cases, and you can say, well, okay, for the conversion of this chemical into that product, the rate is typically between these bounds. And then you can either use the fixed value from the literature, or you can say, well, hey, this parameter tends to be in this range. Let me do an experiment to determine and fix that parameter. So that also gives you a way to fix parameters in your model and then exclude them from further analysis. So either determining them experimentally, if you can, looking it up in the literature, if you can, but either way, coming up with basically a fixed value. So basically what we're doing on this slide is finding ways of having to do less work. We as scientists, we want to be lazy. If we don't have to do the work, if we don't have to spend our night in the lab, or our night in front of the computer trying to debug our model, then we have to be smart. And smart means looking for things where we can simplify our model. And one of them could be determining that either this parameter doesn't have to be estimated because it's not important, or doesn't have to be estimated because I already know its value, and so on. And maybe to finish off this story, so yeah, the third bullet point here says, and let me hide my tools here. So if you can't measure it, what you can still do is you can go to the literature and try to find something out about your parameter, the range that it can vary in, or you can use your chemical or your biological or biotechnical background and say, okay, this kind of reaction rate, this kind of temperature is going to be in this range. So I'm going to fix that parameter to a certain value that makes sense. And how you do all of those things, this is of course very subjective, basically driven by your prior knowledge in the subject area. If you start from scratch, this is going to be difficult, but if you already have something to go on, this might be a way to reduce parameters in your model. And the rule of thumb at the bottom of the slide is, if you can simplify your model to have fewer parameters, that's almost always a good thing. It'll make both the fitting, the finding the parameters, and the interpretation easier. So now we have a set of parameters that we want to estimate. We're happy about that. We've done our sensitivity analysis, and now it comes time to actually fit the model to the data and find out what parameters give us the minimum value for our objective function. So there's going to be two big classes of approaches that we can follow. And one is, there may be a formula that gives us analytically, so a formula that where we plug in some numbers that gives us the parameters. So one possibility is that parameters can be estimated by closed form formula. And what I mean by a closed form formula is basically I can give you a formula where you put in your data and it spits out the parameters. So an example here is the parameters from linear regression, so alpha and beta from linear regression. The other option is that there's no such formula. So in this case, the parameters need to be estimated numerically. And as you can probably guess, the vast majority of optimization problems, of parameter estimation problems, are going to be in the second category. Even it turns out for linear regression, sometimes you don't want to use those formulas that I've given you. If you have a huge data set with millions or billions of points, the closed form formula for linear regression actually becomes quite inefficient, and it can be more effective, more time effective to do the fitting, the parameter estimation numerically. But even so, like we won't get in the realm of millions or billions of data points, but we will quite quickly encounter models for which we need to estimate the parameters numerically. And so when you have to do that, then typically this will be an iterative process. So iterative means that we start with a guess of what the parameters could be, and then we try to change the parameters a little bit to see if we get a better value of the optimal function. So a value of the parameters that decreases the objective function. So typically, if we draw the space in which our parameters live on 2 dimensions, so let's say we have 2 parameters, theta 1 and theta 2, we'll typically start with an initial guess, and then we'll measure the objective function for that initial guess, and then we'll try to change this initial guess a little bit and see if the objective function decreases or not. And we'll do this a number of times until finally we decide, hey, now we have a value of our objective function which we cannot decrease any further. So for instance, if we change the parameters, the objective function changes, but very, very slightly, like one part in 10 to the power 16 or something very, very small, almost negligible. In that case, we say, okay, we're done. We have an optimal value of our objective function. So how do you choose that initial condition here? Or maybe just backtracking a little bit. So we will see a number of methods to do this update, to do this iterative process. And they're going to differ basically on what, like they will have some kind of heuristic to say, oh, you should do the update like this or like this. So that we will see later, but let's talk about this initial point. So here, this initial point. How do we select that? Do we just choose it at random or what do we do? Well, the bad news is that most of these methods tend to be sensitive to how you choose that initial that initial point. So there can be choices where the optimizer has to do a lot of work to sort of start from your chosen initial condition and then bring it to something that actually makes the objective function minimal. So let's say, for instance, you have a chemical process where you want to estimate the rate, and let's say that the true value of the rate is 1 per second. But for some reason, you started with an initial guess of 10,000 per second. Now, what your model will have to do, or what your optimizer will have to do, is have to figure out, okay, 10,000 doesn't make sense for this problem, so let me try 9,999 and see, okay, I have a small improvement, okay, 9,998, and so on, until it sort of gets in the region of your optimal value. So this would probably be a not so great choice of an initial value. The problem becomes worse if you have multiple parameters to estimate. So there, like now you have to make an initial choice for each parameter at a time. And it could be that you manage to choose the initial conditions well for some of them, but not for all. And in that case too, your model or your optimizer will have to do a lot of work before it gets to the right or the best parameter values. So how can you choose the initial point? So that was all the bad news. What is the good news? So the good news is that typically you can again use your knowledge when you build a model. You can say, okay, my kinetic rate is not going to be 10,000 per second. It's probably going to be around 1 per second. Maybe you read a paper and they did a similar experiment and they had 0.5 or 0.9. So you say, I'm going to use 1 as my initial value. So typically you have some domain knowledge to make you guess initial values that are going to be at least reasonable. The other thing that you can do is you can do the optimization a couple of times for different parameter values. And you can observe, well, okay, if I take different initial conditions and I do my fit, by how much do my outcomes, my parameters change? And if you see like, okay, independent of which initial condition that I choose, they all sort of end up in the same region. So let's say I take another initial condition and now my model does some other exploration, but eventually it gives me a final parameter value that is close to the one that I had before. Then you can say, okay, I'm probably in a region of the parameter space where things just work. So I can be confident that what I get out for the parameters are going to be correct. So either one of those is probably going to give you a good initial condition and hence a good estimated set of parameters to work with. And what you can do moreover with the initial conditions, so if you don't have the domain expertise, if you don't have a paper in the literature that tells you an acceptable range of your parameters, the last thing that you can do is you can always use simulation. You can simulate. So you can say, well, if this is my initial condition, if I plug that in my model and I simulate the behavior of the data using the model for those initial conditions, do I get something that looks reasonable? And then you're immediately going to see if your initial conditions make sense or not. They're not going to reproduce your data exactly because they're just guesses, these initial conditions. They're just what you think is right. They're not the true values of the parameters. So your curve is not going to fit the data perfectly, but it should give you some indication of whether what you're doing makes sense or not. So just to wrap that up, let's say you have some data for the Michaelis-Menten reaction kinetics, and let's say you say, okay, based on my understanding of enzyme kinetics, I think Michaelis-Menten constant of 2 per second is going to be a reasonable guess. So this is my initial guess for the parameter. And now if you plug that value of the Michaelis-Menten constant into the model and you ask it, well, draw the curve, and you get something that looks like this, and it overshoots a little bit, that's fine. Like now you know, okay, I'm going to have to ask my optimizing algorithm to change that to 1.5 or whatever it is, but I know I'm in the ballpark. But if you say, well, okay, I'm going to plug in 10,000 per second, and now you get something that looks like this. So it goes up vertically and then flattens out. This is probably not such a good initial guess. So you look at, for your initial condition, you look at what the model would look like. If it's roughly the same as what the data looks like, then you're on the right track. If not, think maybe 10,000 wasn't such a great value. Maybe you should go back to the chemistry textbooks and find a more acceptable value. We will see a couple of examples probably in the practicals where if you choose the initial conditions wrong, you get totally wacky models that oscillate all over the place. So it is important once you both when you start the estimation and when we get your final result, that you look at what the model looks like, and then immediately that's going to tell you whether you're on the right track or not. So another thing that can be at play here is that some parameters may have boundaries, may have certain values that they can't exceed. So for instance, if you want to optimize the working of your bioreactor and temperature is a parameter, then probably the temperature will have to be within a certain range. So maybe when you bought your machine, the manufacturer said, well, okay, you should only operate this in the realm of 0 to 40 degrees. Or maybe if you have a kinematic reaction rate, maybe it doesn't make sense to have a rate that or well, let me backtrack a little bit. So if I have a kinetic rate, I know that's always going to have to be positive. Could maybe be zero, but it definitely cannot be negative. That's just the nature of things. So there are many examples of parameters that are not completely free, but that come with certain ranges. Reaction rates have to be positive. Temperatures typically can vary between fixed bounds. If your chemical reaction goes better with temperature, you don't want to take that to the extreme to say, okay, now my bioreactor has to operate at 1 million degrees Celsius, because that's where the reaction really peaks. You want to keep in mind that, yeah, my reactor can only do 40 degrees or whatever. So I need to cut off my temperature at that range. And so what we want to do is when we do that exploration of our parameter space, then we want our exploration to take place within those bounds. So we want, let's say if we have bounds on theta 1, so let's call this theta min and theta max. We want the exploration of where the best parameters to be. We want this to take place entirely inside this range. Because, yeah, by definition, we know if we go outside that range, we might find some parameters for which the optimal value of the objective function is better, but they're not physical parameters. So now the question is, how can we make that search take place entirely within those bounds that we specify on our parameters? And it turns out that there's two approaches. And the first one is called using a penalty function, which basically means that you just make it very disadvantageous to go outside of the range of acceptable parameters. So you say my cost function is whatever it is, but if you happen to go outside of that range, I'm not going to do anything, but all of a sudden I'm going to crank up my cost function to be really high. It's a little bit like when you were little children, or when I was little children, your dad lets you play in the park and you can wander around in the park and explore yourself. But your dad says, okay, you can't go outside the park. If you go outside the park, there will be a punishment. Like you can't run in the roads because that's bad. And your dad doesn't attach a cable to you so that you physically can't go outside of the park. Your dad just relies, or your mom, on the fact that if you go outside of the park, there will be a punishment, and you know that. So while you're in the park, your happiness function, let's call it like that, is quite high, or your unhappiness function is quite low if we flip the terms. But if you go outside of the park, then you know your unhappiness is going to increase by a lot because your mom or your dad is going to come after you and not going to give you ice cream. And we do the same thing for parameters. We're going to change with this penalty function. We're going to give them basically a penalty if they go outside of the range. And the penalty is going to be very high, which makes it very disadvantageous to go outside of the range. And the other approach is to do a transformation of the parameters, where we basically take the range that they can be in, and we apply mathematical transformation to make that range into the full real line. And then the parameters are free to explore wherever they want, but if we transform back, they're still going to be within that range. So let's see how that works. So first is the penalty function. So this is, again, the example of your mom or your dad giving you a punishment if you go outside of the park. So what we do here is we take our objective function, and we're going to call that J unconstrained. So that is the objective function that we had before. And now we're going to attach to that objective, to that unconstrained objective function, a penalty term. And we'll have one penalty term per constraint that we want to impose on the parameter. So if you say this parameter has to be positive, that's one constraint. If we say this parameter has to be within this range, that's two constraints. That's one constraint for the lower bound, one constraint for the upper bound. If we have three parameters that all have to be within an interval, that's two constraints for each parameter, so 6 constraints total. And the idea here is that the penalty term is chosen so that it doesn't contribute in the sensible region where the parameters can live, but it is very, very high outside of that region. So typically what this looks like is, if I just sketch my penalty function, typically you have something like the following, where if this is my theta min and this is my theta max, I have something that is very, very high outside and then drops off really quickly and becomes either 0 or a small constant in this range. And then for theta max, again, it goes off and becomes very, very high. So this is like this value here of the objective function. How should you choose this? Well, this should be something that is very high to avoid basically the parameter going outside of it. Think a bit what happens with your mom or your dad. If your mom or your dad says, okay, if you go outside of the park, yeah, I might give you a punishment, maybe not. Or I'll still buy you ice cream, but it won't be the best ice cream. That's not a high penalty. So you will be tempted to still go outside. Whereas if your mom says, okay, the moment you step outside, no ice cream for a year, that's a very high penalty. So that'll be very effective at keeping you within the range. And so now that we know what kind of function to use here, let's talk a little bit about what that function could look like. Well, you have a number of choices. You could choose a discontinuous function for the objective function, where you basically just make this pattern, this step pattern, into a real step. So for this discontinuous function, you basically say, my penalty is going to be, so let's say this is theta max right here. My penalty function is going to be exactly 0 for theta below theta max, and then it's going to jump discontinuously to a very high value, let's say 10 to the power 20 outside of that range. And that is good. It's a very simple prescription, but the disadvantage is that it's discontinuous, and that can sometimes give you a problem numerically, because you basically have a penalty that you don't feel until you hit the wall of theta max, and then all of a sudden it's 10 to the 20. And that might throw the numerical optimization algorithm off, because there's no indication that this punishment, this penalty will follow. Again, like you can probably make an analogy with your parents. If you walk outside of the park and all of a sudden your parents are very, very upset at you, you're going to be confused. And likewise, the optimizer is going to be confused if you all of a sudden impose a very high penalty. So what you can do in order to avoid this discontinuity is you can smooth out that transition a little bit, where now instead of making a harsh jump, you basically build in a gradual transition. So you still want to end up at a high value here, but you do so gradually with a certain slope. And the advantage here is that you will start feeling the penalty when you get close to theta max, and your optimizer will have time to adjust to it before it really is in the forbidden zone. The disadvantage is that depending on the slope of this increase, your parameter might end up a little bit outside of the desired region, because if it ramps up slowly, maybe it's not high enough at theta max in order to exclude that. So what you end up doing, to put it in other words, is you soften the slope or the jump a little bit, but as a result, that jump gets softened, which means that the parameters have a little bit more flexibility to maybe stray a little bit in the zone where they are not supposed to be. So that's one approach. Let's quickly look at the other approach, and then we'll stop for a break. So the other approach is to transform your constraint problem into an equivalent unconstrained problem. And to be honest, if you can do this, this is probably a mathematically or numerically more stable approach. So with this penalty function, you're always going to have this very harsh effect of like the system is going to push the parameter back into the desired zone, and that may or may not work out so great. But with this transformation, you end up with an unconstrained problem, and then the optimizer has no problem whatsoever. And all you have to do when you found the parameters is you have to transform them back into the constrained regime. So there's a little bit more work for you, but numerically it's going to be easier. And so what you can do is you can do a number of things depending, again, on what your constraints look like. So for the first example here, we have a parameter like kinetic rate, which has to be positive. So what we can do in that case is we can say, well, if this parameter is positive, we can write it as the square of something. And that something now can be negative or positive, because taking the square is going to obliterate the sign, and it's going to give us something positive. And now that phi, that thing underneath the square, we can ask for the optimal value, because we know if it's negative, no problem, since we still have to square it in order to get the optimal value. Or we can say, well, I'm going to write theta as the exponential of something which can be negative or positive. And depending on what that phi is, I'm going to get small but positive values for theta, or large but still positive values. And that's good, or those are good transformations if you want something that's always positive. If you have something that needs to be within a certain range of values, there's also a variety of transformations that you can apply. And one of them, for instance, uses the tangent function. So how does this work? So let's say you have a parameter theta that has to be constrained between two values, theta min and theta max. You can use the fact that if you remember your tan function, your tangent function basically looks like this. So it has vertical asymptotes at pi over 2 and minus pi over 2, and then like this and like that. Oh, that's horrible. So this is my tangent function. And now I'm going to use the fact that one of those branches has two asymptotes. What I'm going to do is I'm going to draw a tangent function here so that its asymptotes are at theta minus and theta max. So that's going to give me a tan function that looks like this. It's probably going to cross the x-axis here and then go off to infinity here. So I want that green function, and I want to have two asymptotes, two vertical asymptotes, one at theta min and one at theta max. So how do I do that? Well, what I need to do is I need to shift the tangent function by a certain amount, and I need to scale it so that the distance between the two asymptotes is precisely theta max minus theta min. So here, remember, for the original tangent function, the distance between the asymptotes is pi. And for the transformed one, here I want the distance to be theta max minus theta min. And if you think a little bit about how to do that, then you'll probably come up with the prescription that is given here. So what we end up is the tangent of I over 2 times theta minus theta max minus theta min, and then divided by theta max minus theta min. Because if you look at what happens in the limit, so if you let theta go to theta max from the negative side, so we take the limit as theta approaches theta max from the negative side, then what you end up in the argument is 2 times theta max minus theta max, so that's theta max, minus theta min. So you will get something that looks like tan of pi over 2 theta max minus theta min divided by theta max minus theta min. So in other words, tan pi over 2, if we can write down something like that, and that's going to give you plus infinity. And likewise, if you let theta go to theta min from the positive side, then what you'll see is that your function will tend to minus infinity. So this gives you the right prescription basically for a function that reaches minus infinity as theta goes to theta min and plus infinity as theta goes to theta max. And what does this whole function buy us? Well, if we call this function tan of pi over 2, etc., if we call this phi, if we put phi on the y-axis here, then what we basically have is that when theta ranges from theta min to theta max, phi can range from minus infinity to plus infinity. So this is another example of an unconstrained parameter, this capital phi is. We have something that ranged in a certain interval, and we've transformed it into something that can range over the entire real line. So if we now describe our problem in function of phi, then what we're going to end up with is something that is unconstrained in phi. So then we can find the optimal phi value. And once we've done that, we have to transform it back, which means basically undoing the tangent function. And you have the prescription for that here. So you take the inverse tan and then you scale and shift according to what is given here. Okay. So I will stop here. We will take a short break, maybe a 10-minute break until it's 11:25, until 11:35. And then we'll continue, have a couple more slides to go through. And then we'll stop with maybe half an hour-ish of discussion about the exam. So see you again at 11:35. All right, everybody, we're back. The recording is started again. So for the remaining hour or so, we'll wrap up this section and then also mention a bit about the exam as announced earlier. So before we get into the details of the actual estimation of the parameters, there are a few more concepts to cover. And one of them is identifiability. And what do we mean by identifiability? Well, this is basically the question of, can we find a unique value for each parameter or not? And if we can find a unique value for our parameters, then we say that the model exhibits structural identifiability. So again, this means we can find one value and one value only. And this is going to depend on a number of factors: on the model structure, so how the parameters appear in the model, on the choice of parameters that we want to estimate, but also on the data. And this last part we're going to see in detail is basically related to what is the quality of the data, and what data do you have available. For instance, very stupid example, if you don't have any data for a certain parameter, then you're not going to be able to estimate it. So then you may have structural identifiability, or you will not have identifiability. And how does models that are not identifiable manifest themselves? Well, if you have different combinations of parameter values that give you the same output, for instance, if you have correlated parameters, or if you have parameter estimates that come with very large confidence intervals attached to them. So meaning parameters that can basically vary over a wide range of values without affecting the model too much. So those are the two telltale signs that maybe your model is not identifiable. And so to make this a bit more concrete, we have an example. And to get there, we can basically be a little bit more precise. So I mentioned that the identifiability depends to a large extent also on the data that you have available. And it can be that you have a model where a priori the parameters are all nice and well determined, or can be determined, but the data is not of sufficient high quality to allow for that determination to happen. And to give you an example, here is a very simple model where y is a times x1 plus b times x2. And a and b here are the parameters. X1 and x2 are the predictors, and y is the outcome. So if we can measure x1, x2, and y, and if we have sufficiently many data points, then we can determine both a and b. So for instance, if I have two parameters, if I have more than two observations for x1, x2, and y, then I get a system of linear equations for this model, and I can find a and b. So this model is structurally identifiable in the sense that given enough data, I can find the parameters. But now imagine that my data collection process isn't completely what it should be, and I can't measure x1 and x2 independently. I can only, when I do my measurements, my sensor gives me x1 equal to alpha times x2. So what I have is, if my data set has that kind of correlation, then basically my model becomes ax1 plus bx2 is equal to a times alpha plus b times x2. And now you see I only have one independent predictor, x2, and I get a combination of my parameters, a combination that involves both a and b. So now, knowing x2 and knowing y, I can find this combination here, but I can't pull that apart to find a and b. So this model is practically not identifiable because my data that I gathered is not sufficiently broad to allow for identifiability. And here is another example of a slightly more complex model where now we have three parameters A, B, and C. And you can see if you rewrite this model to factor out the x1 and x2 that you get combinations of parameters A plus C x1 plus B plus C x2. And here too, you see, because you have those combinations of parameters, this is a model that's now not structurally identifiable. So even if you have perfect data for x1, x2, and y, so data that's all over the space of admissible values, what you can determine is this combination A plus C and this combination B plus C, but you can't use that to pull apart those combinations and figure out A, B, and C independently. So what you can do here is, this is of course a very synthetic model, but maybe there's something in the domain that allows you to fix one of those values, A, B, or C. Maybe there's some paper where you can say, well, okay, C is typically always 2, so I'm going to fix C equal to 2. If that's the case, then now you have 3 relations. You know what A plus C is, you know what B plus C is, and you have this new information, C is equal to 2. So that then allows you to find A and B as well. So even if your model is structurally not identifiable, maybe there's some extra information that you can add to make it identifiable. And then once we have all that, there's a little bit that we can say about the residuals as well. So we're going to look at the residuals of our model to figure out what the fit, whether we have a good fit or not. And the residuals basically tell us something about the measurement error when we acquired our data. And some of the selection criteria for different models, and we'll see this later on, but this was also already the case for linear analysis, depend on looking at the residuals. So you remember from the output of a linear regression analysis, we also looked at the residuals, the distribution of the residuals to figure out, do I need to include more terms in my model, or is it, does it look like random noise? This is weird. Okay, sorry, my iPad was frozen for a second. So many of the same considerations that we made for linear analysis, for linear regression, are also going to apply when we look at the residuals of more general models. So in particular, we'll assume that if we have an outcome Y, that the measurement errors, that the noise on that outcome is normally distributed with mean 0, with constant variance, so homoscedasticity, and that the outcomes or the data points were acquired independently. So you can ignore this part for the time being. And so when it comes to looking at the distribution of the residuals, there's going to be one more tool that we can use in addition to linear models. And this is going to be important when we have a model where the predictor is actually time. So many models predict something that happens over time as a function of time. So we basically make a prediction at, let's say, 1 second apart. For instance, we have a bioreactor and we have a model that describes the concentration of a certain chemical as time progresses. So here we have a class of models where the predictor or one of the predictors or one of the input variables is time, and the outcome is a physical characteristic, concentration, or whatnot. So when we want to look at the residuals, what that means is that now we have residuals basically as a function of time. And what we want to see is the same thing as for linear regression analysis. We want to see no significant change in the distribution of the residuals as time progresses. So we want to see no trend. We want to see random residuals as time progresses. And on the slides on the bottom, you have two pictures, synthetic data. So I made this data. On the left, you have randomly distributed residuals as a function of time. Sorry, on the left, that's random. And then on the right, you have residuals where there is some kind of trend. So in particular, you see that residuals sort of go up first and then decrease and become negative and then maybe increase a little bit. So here you do see a certain trend. And when we look at the fit of our model, we want to see that the residuals are randomly distributed, because we know, yeah, there's going to be some noise, so we will see some residuals. The residuals will not be zero, but if there's a pattern, then again, we know there's something that we didn't capture in our model. So how can we measure this correlation between the residuals? Well, an additional tool that we will use is the so-called autocorrelation function. And what this is going to do is going to basically shift our residuals around and then see whether a shifted version of the residuals looks like the original or not. And this mathematical expression, we're going to come back to that, but I want to first show you a example on a different kind of problem. So here, and this is one of the new slides that I inserted. So from this point, it becomes a little bit different. What we have here on the left is the energy consumption of residential and commercial properties in Korea from the year 2017 to 2019. So we have about 24 months worth of data, the energy consumption in thousands of tons of oil equivalent. So some measure of energy. And if you think about that signal that you see on the left, this has some very physical characteristics that you would expect. So you see, for instance, that the energy consumption is highest in the winter in January. And here too, we see it's very high in January. And then it flattens out in July, when or slightly before, maybe in June, when the weather is good and the temperature drops. And also, I don't know if this is a signal or if this is actually noise. You see a slight uptick here in August. I think that is when everybody is turning on their AC and using a lot of energy just to cool themselves down during the hottest days of the year, but that might also be just a fluctuation. The important thing is that you see in this signal this nice year-by-year trend. And so we can understand this repeating trend in the data by looking at the autocorrelation. And this is what's shown on the right. So on the x-axis here, we have the autocorrelation, and sorry, on the y-axis. And on the x-axis, we have the so-called lag. What does that mean? Well, what we do is we will take two versions of our data, and we will shift one of them by a certain lag. And that lag can be 1, 2, 3, and so on. And then we will compare the shifted version with the original signal that we had. So if I sketch that, what we do is we take two versions of our signal. So this is the original one. And now we take a shifted version like so. And the amount by which we shift, so let's measure it from the peak here to the peak here. So this amount that we shift by, this is called the lag. And now we compare those two signals. And the way that we're going to compare them is we're going to multiply the data points from the original signal with the data points from the shifted signal and sum up all of those multiplications. And what that does is, if you have two signals that look very much like each other when you shift them by a certain amount, then you get two sets of observations that are almost the same. So when you multiply them, you get very big numbers. And when you sum them, you get an even bigger number. So this will give you a correlation that's very high. So high correlation means, or high autocorrelation means signal looks like shifted version of itself. And now let's think about that from a physical perspective. If I take the Korean power consumption and I shift it by 1 month, that shifted signal is probably still going to look a lot like the original version. It's again 2 peaks, slightly offset. So what that means is that the correlation is going to be, or my correlation is going to be high. If I shift by 2 months, that signal still looks like the original version, but the peaks are already a bit separated. So that signal looks okay like the original version, but not as much as just shifting by 1 month or by 0. So the correlation is going to be a bit lower. And if we shift the signal more and more, the power consumption in March doesn't look like the power consumption in January. The power consumption in April doesn't look like the power consumption in February. So if I make that lag bigger, then the 2 signals start looking different, more and more different, and the correlation goes down. And you see this in the plot here. And actually, there's something wrong on the x-axis. I will correct this in the slide, but all the lags here are offset by 1. So this should be 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So lag 0 means we just compare the signal to itself. It's a perfect copy. So here the correlation is going to be very high. It's going to be normalized to 1. Lag 1, so offset by 1 month, looks like the original signal, but not as much as an exact copy. So the correlation is already a bit lower. And then the more we shift and the more we compare 2 months, 3 months, the less correlation we have, until finally at 3 months, the correlation starts becoming negative and then increases until 5 to 6 months. And here the correlation, the autocorrelation is very negative. And what does that tell you? Well, think about power consumption patterns. The power consumption in the summer isn't the same as the power consumption in winter, but it's almost an exact replica of the winter power consumption, but it's the opposite. So if you use a lot of power in the winter, you're going to use little power in the summer, year by year. And that's what this negative autocorrelation tells you. And then if you keep shifting the signal past 6 months, so 7, 8, 9, the correlation starts increasing again. So the power consumption in October is probably similar to the power consumption in January, the one in November even more, until when you hit 12 months here. So for 12 months, we see again a peak in the correlation, which basically means the power consumption in January of this year looks very much like the power consumption in January of last year and the year before that. So what the correlation function, the autocorrelation basically tells you is something about the periodicity in your residuals, or more generally in your data. So if it's high, it means that you can shift the signal by 12 months and not see that much difference. If it's low, but if it's negative, very negative, then it means that you can shift the data around by that many months and see the exact opposite of what you saw before. So for instance, for 5 or 6 months here, our original signal might look like this. So this is January, and then this is January again. And if we shift that by 5 or 6 months, we get something that's high when the original signal is low, and low when the original signal is high, and so on. So we have, as the 2 signals are out of phase. So that's the background behind the autocorrelation. Now let's look at the formula and how this is applied. So what we're going to do to compute this quantity is we will take so now we're going back to, forget about power consumption, we're going back to residuals. We'll take the residuals as a function of time, and we want to figure out, is there some trend in the data? Is there some periodicity in the data or not? So we're going to take the residuals at a certain time and multiply them by the residuals at a later time. And here this tau parameter is the lag. That's going to control by how much we want to shift the residuals. So here we have n, big N data points, so n residuals, and we take the original residuals. So let's draw some residuals. Let's say we have 5 like this. So this is 1, 2, 3, 4, and 5. And now let's say tau is equal to 2. So we make another copy of that signal, and we shift it by 2 towards the left. So here we take and we make just a little bit of space. So we shift it by 2 to the left to get 1, 2, 3, 4, and 5. So that's shifted by 2. And now we're going to multiply 1 with 3, 2 with 4, and 3 with 5. We're going to multiply all of those. So those are the terms that we have here inside the sum. And then we sum up all of those contributions. And to normalize, what we do is we divide that whole thing first by the number of points that we summed over. So here n is 5 and tau is 2. So we're going to divide by n minus tau. So that's 3. And we're also going to divide by the autocorrelation R for lag 0. So this 1 over R0, R0 is the sum over the squares of the residuals. So here you take the sum, you take all the residuals, you square them, you sum them together, and you divide by n. And that's going to give you exactly the quantity that I showed you on the previous slide. And so to summarize, what does this give you? So there's a number of conclusions here to draw. So first of all, the autocorrelation is always going to be between -1 and +1. Why? Because of this normalization, because of the fact that you divide by the correlation at time t is equal to 0. Secondly, the correlation, the autocorrelation can be equal to +1. And what does that mean? Well, this means that residuals look like residuals shifted over tau units look exactly like original residuals. So if you have a sign pattern in your residuals, then you can shift them by 1 period, and you're going to get something that looks very similar to the original signal. So for that, your autocorrelation is going to be high, close to +1. And the opposite also can happen. So the autocorrelation can be -1 or close to -1. And in this case, the residuals shifted over tau unit look like a flipped copy, so a negative copy of the original residuals. So look like the negative of original residuals. So I know that this is a bit abstract and a bit vague. Keep the Korean power consumption in mind. If you shift the power consumption by month over 12 months, you're going to get something that looks exactly like what you started from. So there, the correlation for 12 months is going to be high, +1. If you shift it over 6 months, then now you've aligned the winters with the summers. So it's going to look very similar, but it's going to be anti-correlated. When it's high in the original signal, it's going to be low in the new signal and vice versa. So here the correlation is very negative, very close to -1. So this means anti-correlated. Now keep the example in mind. That's also how I reason about this. So now we can use this to say something about whether we see some trend in our residuals or not. So I have again the two plots from the first slide, random on the left, correlated on the right. And now let's look at the autocorrelation and see if we can observe something from here. And once again, I do have to apologize. The axis labels here are offset by 1. So this is 0, 1, 2, 3, and so on. And likewise here, this is 0, 1, 2, 3, and so on. So they don't start at 1, they start at 0. And we'll scratch them out just so. So if you look at the autocorrelation plot, so for each lag, for random residuals, then you see there's basically one high correlation at 1, and that's for if the lag is 0. And this is always going to be the case. So lag 0 means you compare a perfect copy of the signal with itself. So two perfect copies of one thing are going to be very strongly correlated. So you will always have a peak for lag 0. So here you also see that peak on that. But then if you compare the two plots, then you see that the autocorrelations on the left are basically randomly distributed. Some of them are positive, some of them are negative, some big, some small, but there's no pattern here. And if you compare it to the right, so here we do have a correlation in the residuals. We have that trend like so. And we see that there's also a pattern in the autocorrelation. So we see the autocorrelation sort of falling off and gradually diminishing as there's less and less memory. And it turns out we're going to use that information to say something about these residuals are correlated with one another or not. So it turns out that you can say something about the distribution of the autocorrelations themselves, and they end up following a normal distribution with variance 1/n. So the autocorrelations basically follow a normal distribution with mean 0 and with variance 1/n. So variance 1/n with n the number of data points. And so what we can do is we can use that information to say when does this plot look not random at all. And so here, for instance, what I see is that I have an initial peak and then it's sort of gradually drops off. So that definitely does not look random to me. But we can turn it into can make it a bit more quantitative. What we can say is that if I want to be 95% confident that residuals are not, or sorry, that correlations are not randomly or not normally distributed, normally distributed, what I can do is I can look at the 95% quantile of my distribution. So remember here, the variance is 1 over n. So the 95% quantile is going to be minus 1.96 times 1 over square root of n up to plus 1.96 1 over square root of n. So that 1.96, that's the 95% quantile from the standard normal distribution, but here my variance is 1 over n, so I have to scale everything by 1 over square root of n. And so I can look at that, that interval, and then I can count how many autocorrelations do I see outside of that interval. So that's what the red bands indicate on the plot. So this bound right here is 1.96 times 1 over the square root of the number of observations. And I think I had 50 here. Does that make sense? No, I had 25. Yes. So that's 1.96 divided by 5. So that's about 0.4. And then here I have minus that value, so minus 1.96 divided by square root of 4, so about negative 0.4. So the red bands basically tells me what, like, gives me that 95% quantile. So, okay, now I have that band, and what does that tell me about my autocorrelations? So now I can count. It's a 95% quantile, so I want 95, or I expect 95% of the autocorrelations to be within that interval. And now I can already see that that's not going to be the case, because I have 1, 2, 3, 4 that are outside. So 1, 2, 3, 4 that are outside out of 17 in an interval. So 4 out of 17 is much more than 5% that I would expect to be out if it's really normally distributed. So in this case, this is an indication that my autocorrelations are not randomly distributed, and that therefore I have some trend in my data. So here we have the number. So we want to have 95% confidence that our correlations are randomly distributed, which means we have to look at the 1.96 quantile, and we want maximum of 5% of the autocorrelations to be larger than those thresholds. So here, as I mentioned, we have 4 out of 17. So that's 24%. That is higher than 5%, obviously. So therefore, we decide the autocorrelations are not randomly distributed. Therefore, the residuals are not independent. So this gives us a quick and easy test to look at, are our residuals randomly distributed or not? In R, you can easily compute the autocorrelations with the ACF commands. So that's also worth knowing. So you give it the vector of residuals, and it'll give you either this plot or the raw data. Okay. So I think we have about 5, maybe 10 minutes if you want to play it a bit close to finish up this section, which is not going to work. Let me maybe just say one thing about actual parameter estimation, and then leave the rest for next time. So one more thing to add to the autocorrelation section here is So what do you do if you have a signal where this test tells you, hey, there's correlation in your residuals? Well, what you can do is you can subsample the data, and here you use the number of significant lags to see what amount of subsampling you have to do. So with the signal I showed you, there were 4 significant lags. So we're going to keep 1 out of every 5 data points. And if you do that, so you keep every 5th data point, basically, you get a signal that looks like that. So residuals that look like the left. And now if you look at correlations, you see that, yeah, they look much more random than before, and you see much less correlation between the individual residuals. The disadvantage is, of course, that you have severe loss of data, so you end up with basically 20% of your original data set. So in most cases, this is very painful. What you can do if you don't want to subsample is you can use the fact that there's some structure in your residuals and explicitly model that. So add some interaction terms or some higher order terms or correlations to your model, and then use all your data. But that falls a bit outside the scope of this course. Okay, so we covered this example. And then maybe to wrap up here, and we'll continue with this next time. So now we have all the everything that we need to minimize our cost function. So once again, we're going to look for a theta that makes our cost function as low as possible. So we're trying to find a theta hat that minimizes that objective function. And how are we going to do that? Well, there's many different algorithms, many different approaches. But one thing that we can do is we can use our intuition from multivariate calculus. And we can say, well, where do we find a minimum of a function? Well, we have to look at the points for which the derivative or the gradient vanishes. So in 1D, this is easy to see. And I think you remember this from calculus very well. So if you want to find the minimum of a function, then that's going to be the point where the derivative vanishes, where the tangent line is horizontal. So if this is f of x, then the minimum is going to have that. If this is x0, the minimum, then that's going to have the first derivative equal to 0. If you have a objective function of more than one parameter, so several parameters, then there's no longer one derivative to calculate. So now you have to calculate derivative with respect to each parameter. So you get partial derivatives of j with respect to each parameter. And you look at where those partial derivatives become 0. So there's a small calculus thing to be aware of here. If you look at this system of equations, partial derivative equal to 0, what you will get is that you will get the theta that are critical points. So the solutions of this system are the critical points. So they could be minima, maxima, or saddle points. So neither minimum or maximum, but you know the minima are going to be part of those critical points. So you can check which one is minimum, which one is maximum. In practice, it turns out that this is not really a problem. Like the numerical algorithms will converge to the minimum because of numerical stability. And if you look at this system of equations, partial equal to 0, then you can have two things, as I mentioned before. Either you get a system of equations that you can solve explicitly, or you get something that you have to solve with the computer. And it turns out that for linear regression models, you can do that explicit calculation as we've done. But for nonlinear models, you'll typically get something that is not explicitly solvable, that is that requires some numerical implementation. So I will skip over this, so I will not cover this slide. So here we come back to the linear model in matrix notation, and then we do the explicit, like we take the partial derivatives and come up with the function for the explicit parameters. So I will skip over this as well. This is just an example to show that for a linear model, yes, you can find the parameters explicitly, but you already know that from the previous section. And then here we have another model, and I will leave this also for you to review, of an objective function. So here y is equal to x to the power theta. So the parameter appears as a power, and the objective function is still the sum of the squares of the residuals. So you take the y values and you do minus xi to the power theta. And so if you try to find a theta value, an optimal theta value, by taking the derivative with respect to theta, you get this expression, and then you can clean that up a little bit and get the expression at the bottom of the slide. But this is not solvable explicitly for theta. So this does not give you an expression for theta that you can explicitly solve. So not explicitly solvable for theta. So here, what do you do? Well, okay, now we have to use the computer to solve this equation and find theta. And how are we going to do that? Well, that's going to be the topic of the next section. And so just trying to make a judgment call about what to do next. So I want to at least show you gradient descent, which is going to take me about 10 minutes. So what I would propose is that we finish the lecture at 12:30, so in 10-ish minutes from now. And then at the end, I will spend 15 minutes on an exam question. If you want to drop off and have lunch at that point, you can. This will be recorded and you can watch it again if you want to. But if you want to stay on, then of course you can stay on and watch me say something about one particular question from the exam. Okay, so with that, and sorry for the adjustment, but I do want to make sure that you have at least one method for the PC practical on Thursday. So what we're going to do is, now we have a model where we can't find the parameter explicitly, we have to find it numerically. So that's going to be an iterative process. We'll have to start from an initial choice and then make it better, and then see if we're done, and if not, make it better again, and so on. So there are many different methods to do that, but they all share one characteristic, or many share a common characteristic, and that is that they sometimes don't give you the overall minimum, so the absolute lowest value of the cost function, but they can give you what is a local minimum. And what that means is that also for 1D, you can observe this. So you may have a function that looks like this, where the algorithm gives you a local minimum, which is different from the global minimum here. And you see this in 2 dimensions as well. So for linear regression, actually, you can mathematically show that there's always going to be only one minimum, and therefore it's local and global. So no problem there. But for nonlinear methods, for more involved cost functions, the function might have several local minima, and the numerical methods will give you one, but you basically have no control over whether it's the local or the global minimum. Okay. And all of the algorithms are going to do this iterative thing that I've already mentioned a couple of times. They will start with a guess, and then they'll try to find a direction in which to go to improve the estimate. And so every method has at its core an update rule where you take the initial parameters and then you improve them by a little bit, and you try to get a better estimate. And by how much you improve them, that's measured by this parameter alpha k here, and we'll call this the step size. And this could be fixed or it could be variable. And as I already mentioned a couple of times, you have many different minimization algorithms, and people have come up with tons of them already in the history of numerical analysis. And they basically differ in what kind of information they use. So we will distinguish between two broad classes of methods. We'll look at gradient-based methods, and then the rest, so methods that are not based on the gradient. And gradient-based methods, as the name indicates, they're going to use information about the derivative of the objective function. And non-gradient methods are not going to do that. And now you might wonder, well, why would you, like, if you can use a gradient, why wouldn't you use it? Well, the answer is sometimes it's very difficult to compute the gradient of the cost function, and sometimes it's even impossible to compute that gradient. Some cost functions are not differentiable. So for instance, remember the penalty function that we had early on with that jump? So that's not continuous, also not differentiable as a result. So their gradient methods are going to run into trouble. And so for the last thing for today, let's have a look at a very famous method called the method of steepest descent. And this is one where I think you should know the intuition because it's simple and it occurs in a lot of different areas, application areas. And the intuition is very simple. So let's say you're like this person that's standing on a cliff on top of a mountain, and you're sort of hungry. You want to go down in the valley to have lunch, but you want to go down as quickly as possible. You want to take the shortest, or you want to go as quickly as possible into the valley. I'm not going to say shortest path because that's not correct, but sort of like you don't want to go along the ridge just straight into the valley. How do you do that as effectively as possible? Knowing that on top of that, you're very unlucky. There's fog around you, so you can't see, oh yeah, the village is there. I need to walk in that direction. Well, one thing that you can do is, if you're in this situation, is you can look around you and you can look into for the direction of steepest descent. So you can sort of go over the edge of the cliff and go straight down. And chances are, if you don't break your bones, that's going to get you into the valley by the most efficient path, whatever the circumstances. You can also see this if you look at a map. So if you look at a map, typically for a topographical map, you have contour lines like this. So your map might tell you something like this, and then you may have another peak here. And so if you're standing on top of the peak here and you want to descend as quickly as possible to the valley, let's say here, then what you would do is you would walk in the direction of the steepest descent, like so, maybe like so, and then arrive at your goal. You would probably not. Yes, here it's a bit. I could have drawn a better map, but I'll leave it at that. So you walk in the direction of steepest descent. That's going to get you into the valley as effectively as possible. And so mathematically, how can we exploit that intuition? Well, we know something about the objective function and especially about its gradient. We know from multivariate calculus that the gradient points in the direction of steepest ascent, and therefore minus the gradient points in the direction of steepest descent. So in particular, let me try to sketch a little bit better functions. So if I have two parameters, x and y, and I look at the level sets of my objective function, my level sets might look like this. So this might be level set associated with value 10, 20, 30, and then 40 here. And mathematically speaking, I know that my gradient is going to point in the direction in which the cost function increases the most, and it's going to be at right angles to these level sets. So if I want to increase my function, I have to walk along the gradient. And if I want to decrease my function, I have to walk opposite of the gradient. I have to walk along negative the gradient. So the method of steepest descent is going to do exactly that. It's going to use minus the gradient to point out in which direction should I change the parameters to decrease the optimal function as much as possible in one go. And so this gives us the following method, where we start with an initial guess for our parameters, theta k, and then we subtract from that a multiple of the gradient. So minus the gradient again, because we want to decrease the cost function. And this alpha k, that's going to determine how big of a step are we going to take along the gradient. Are we going to take small steps, or are we going to take big steps? And this step size, we can be very simple, and we can say we're going to make that very small but fixed. That's going to give us a very simple method to implement. Just always do the same thing. Compute the gradient, multiply by 100, 1000, and then add that to your parameter estimate. Or we can make that variable to say, well, I'm going to take big steps when the cost function doesn't change a lot. When the objective function doesn't change a lot, I'm going to take big steps. And when it changes a lot and I have to be careful that I don't go up another hill, then I'm going to take small steps. So you can make that into an adaptive method as well. How you choose that alpha k, we're not really going to go into detail because R will do that all for you. And so on the center of the slide here, you have the update rule. So this is what you do at each iteration. And you do that a couple of times until either your parameters don't change very much or your cost function doesn't change very much. So at that point you say, okay, I'm almost done. I must be at a critical point at a minimum of the objective function. And here you see an illustration on a quadratic function, so one that has circular level sets, adaptive method on the left and fixed step size on the right. So here you see we take big steps initially, so from 1 to 2, and then we change the step size 2 to 3, 3 to 4, 4 to 5, until eventually we're going to end up right in the middle of the plot where the minimum is. So you see we take smaller and smaller steps as we get closer to the minimum. On the right, you see we have fixed steps. So that's an easier method to implement if you were to implement it yourself. But you see what happens is that you get close to the optimum, which is again at the center of this circle. But then you take small steps, but you tend to overshoot a little bit. So you have qualitatively different behaviors. So you get close to the maximum, but not as close as the adaptive method does. And then to finish off, the method of steepest descent is very simple, but also has some disadvantages. And that is that it can, for some objective function, it can take a very long time to converge. So here we have a function called the Rosenbrock function, which is sort of made to be hard to find the minimum of. And the minimum actually lies somewhere here. It has a unique minimum, and it's very, very well hidden inside this blue valley. So it's one of those points inside that narrow valley. And if you look at the right here, if we start with initial guess 1 minus 0.5, then you see we apply gradient descent a number of times, and after 1,000 iterations, we're not even close to the optimal value here. And it's going to take tens of thousands of iterations before we even get there. And that's, of course, going to take a long time, and it's going to be not efficient. And you see, we sort of zigzag towards that path, and at the end, we sort of spend all of our time exploring this value, but not making a lot of progress. So the method of steepest descent has its advantages. And as a result, people came up with other methods that we'll talk about next time. And the method of Newton is going to be one example in particular. And just to skip ahead one more time, if we look at the same function that the steepest descent did so poorly on, the method of Newton is going to get so close to the objective that you can't even distinguish it in just 3 tries. So you start with a random guess, you do the method of Newton 3 times, and you get right at where you want to be. Not on the dot, but very, very close. Okay, so we'll talk about that next time. And I'm going to stop talking for about 1 minute here. So we have about 10 to 15 minutes left. I want to say one thing about an exam question, a hypothesis testing question. But as I mentioned, for those of you that want to drop off and have a lunch, feel free to do so. So for those of you who are still here or who will watch this later, that's not a problem with me. I want to quickly have a look at question 2 from the written exam. So you have this on Ufora. You can look at it while we talk. I want to go over this because it's a typical example of a hypothesis testing question that you might have on the written exam. So this is a problem about a beer brewer that makes beer that has 5% alcohol. And he or she does quality control process to check that there is indeed 5% or more or less in the bottle. And on a sample of 40 bottles, they find that the measured alcohol percentage is 4.83%. And we also know from the way that the beer is produced that the variance of the alcohol percentage is 3.60. So now the questions are basically, well, run a hypothesis test to check whether the mean alcohol level per bottle is different from 5%. Write down the null and alternative hypothesis, compute the test statistic, and then basically run the tests, calculate the p-value, interpret what the p-value means, and draw a conclusion from that. So for this, you cannot use R, you cannot use your computer, you can use a small calculator, sort of just basic arithmetic, but no computer. So you need to know how to do this hypothesis test optionally with your course notes at hand. So those are the first 3 points. And then the last 2 are about the power of the test. So what effect size could we detect? And what percentage or what is the probability of finding an effect given the parameters of the experiment. So let's look at each of those in turn, and I'm not going to solve them completely, but just give you an indication of where to look. And let me just grab my notes. So for the first part, yeah, we have our null, and so what test can we use? So here we basically have a one sample t-test or a z-test. So normal, if you assume that the sample distribution is normal, but a one sample t-test would be good. What would we use for the null hypothesis? So the null hypothesis is that the mean beer level, mean alcohol level across the population of all possible beer bottles is 5%. And the alternative is that it's not 5%. So in this case, you want to use a two-sided test because the alcohol level could be higher or it could be lower. You have no a priori indication to say it's going to be lower or higher. And then the test statistic. So for the test statistic, what do we have? Well, the test statistic is going to be the mean minus the population parameter divided by the standard error. And we have some, but not all of those data. So we have that the mean was 4.83%. The population mean is 5%. And now the standard error, well, what is it? So I know my variance was 3.60. That is something that I know from the givens. I have 40 beer bottles. So the standard error is going to be the square root of the variance divided by the number of samples. So square root of 3.60 divided by 40. And that's going to be 0.3. So with that, I can put everything together. I get 4.83 minus 5 divided by 0.3. And if I calculate that correctly, that should give me minus 0.566 and so on. So not difficult, but you have to know which test to use and what everything means in it. From the z-value, you can already see that this is probably not going to be a significant result because we know our threshold for normal distribution is 1.96. If we have z-values bigger than that, then at a 5% significance level, that's going to cause us to reject the null hypothesis. But here, we are much less than that, so probably not going to be a significant test. So then the next question is, yeah, run that test and tell me something about how you could use that knowledge to reach a conclusion. So this is not so much about the calculation, but more about explaining what you're going to do and why that is relevant. So the main figure here to keep in mind for all of hypothesis testing is we basically want to say something about the p-value. So the p-value is the probability of, and I will write it out in words, the probability of data at least as extreme as given data, given that the null hypothesis is true. And so if the p-value is small, that means that it's highly unlikely to see data by chance if the null hypothesis is true. So therefore, we reject the null hypothesis. And the converse, if P is large, larger, then it is somewhat likely or highly likely to see the data occur by chance, and therefore we do not reject the null hypothesis. And the sketch to keep in mind is the sketch of the sampling distribution. So if we look at the sampling distribution, we typically get a t or a normal distribution with mean 0 and with variance 1. And then we have our critical values. So let's say at the 5% significance level, then we have the threshold Z 0.975 and minus Z 0.975. And if our test statistic is beyond that, so if our test statistic is here or here, then we reject the null hypothesis. So let me just say, yeah, this is the area where we reject H naught, and then likewise here we reject H naught. So when our test statistic is beyond these values. And how do we find these cutoffs? How do we determine them? Well, we want 95% of the area under the curve to be between these two bounds, and we want 2.5%, the remaining 2.5% here and here, to be outside of those bounds. So you can make that a bit nicer. I'm going very quick here because I want to get to point number 3, but it's basically explaining what you will do and how you will get there in the context of the problem. And then the actual computation is quite straightforward. So we've already ascertained that our p-value is the probability of having data that's at least as extreme as what we observe, given that the null hypothesis is true. And here we have to be a bit careful. It's a two-sided hypothesis test, so we can have that the data is less than or higher than what we see. So if this is our sampling distribution, and now if this here is our test statistic or the absolute value of it, and this is minus our test statistic, then the p-value is going to be the sum of these two areas. So it's going to be the probability that my test statistic is even bigger than what I see, plus the probability that it's less than in absolute value than negative my test statistic on. There should be Z everywhere. Z, 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 Z. And by symmetry, I can write it as 2 times the probability that Z is bigger than absolute value of Z. And now if you plug in the numbers, and here you have to use your table, then you should find that you get about 57.09%. So we do not reject H naught. And then just to wrap up, for the last 2 problems, I'm not going to work out the exact details. I'm just going to show you the formula. If I can pull it up from my course notes real quick. So for the last part, we have to say something about the power. Bear with me 1 second. Okay. Yeah, so what is the power? Reminder, and this is a very important concept, so you should review it. So the power is basically the probability of rejecting the null hypothesis if the alternative hypothesis is true. So power is probability that we reject H0 given that the alternative is true. And there's a derivation that I will not repeat here, but basically the power is related to the effect size, the number of samples, and the variance. And the key formula here is that the number of samples is equal to Z1 minus alpha over 2 plus Z1 minus beta. And then square of that times sigma squared divided by mu0 minus mu1. And what does all of that mean? So let me take another color. So here alpha is your significance level. So for example, 5%. Beta is your power. Sigma squared is your variance. N, of course, is the number of samples, and mu0 minus mu1 is the effect size. And using all of this information and the data that you have from the problem, you can plug everything in and you can solve for beta. And that should give you that your power is 8.17%. So very low power. So probability of rejecting the null hypothesis of only 8%. Probability of proving what you set out to prove of only 8% if the alternative is true. And then the last part is if you want to have 80% power, 80% certainty, how many samples do you need? So it's the same formula, but now you have to solve for n. You have, so given beta is 0.80, find n, and using the same formula as before, you will get that n is 980.1. So if you run it up to the nearest or to the next highest integer, you will have to test 981 bottles of beer. So that's one question. I selected that one because it's a hypothesis test. You probably don't think a lot about hypothesis testing because that's material from semester 1, but that will be a very significant part of the exam in June. So do not neglect that. Do review it. What we'll do next lecture is we'll do another problem from the same exam. We'll do one of the computer problems. Also a hypothesis testing question. So again, to sort of put that in perspective a bit more. So with that, yeah, I will stop my broadcast. And that is officially the end of the lecture. So thank you for bearing with me. And I will see you again next week on Tuesday. So thank you, everybody, and have a good rest of your day.